All right. So what we have just did in class, at least for me, we just did it. If not, whenever you watched it, what we finished off with in class is if I give you a definite integral and I have a constant as my function, then we can evaluate this by taking this constant value of 7 and multiplying it by our dx. Our x values are your limits, the upper and the lower limits. Let's say this is a 2 and a 10. The difference in x would have been an 8. We multiply 7 and 8 together, and we get our 56. So that's how we can do this if this is a constant. Well, if you look at these problems, 14, 15, 16, and 17, this obviously is not a constant, so we're not going to be able to do it that way. We can't take the expression x plus 3, multiply by 2, and get a numerical value for our area. So what we're going to do is use what it says here as the graph. So think about y equals x plus 3. That's the function we're dealing with. That means we have a y-intercept of 3 with a slope of 1. So if I were to draw that in, that's the function that we're looking for. And this all goes back to the idea of rectangles and area, all this and that. We're looking for the area enclosed by x plus 3 over the interval of 0 to 2. So here's 0, here is 2. Whatever the area of this region here is, that's the answer to our question. Well, if you look at it, we could really do simple geometry to calculate what this is going to be. If you could do a trapezoid, if you remember how to do a trapezoid, we're actually going to do trapezoids in due time. My guess, most people don't. So what we would instead probably want to do is break that into a rectangle and a triangle. So this rectangle here, you have a base of 2 and a height of 3. So this rectangle would have an area of 6. If you go to your triangle, you have a base of 2 and a height of 2. That's 4, but in a triangle, it's 1/2 of your base and your height. So this would be an area of 2. So this value has to be 8, 6 plus that 2. Also, I probably should read these directions and make sure we're understanding this. We are evaluating these. So that's looking for the value of. In this instance, our value and our area would be the same. It's all above the x-axis. So the value and the area would both be 8. But ultimately, eventually, when we do the value and it's not all above, we're looking for the area that's positive above, negative below. We're going to add them up. Okay. 15. If you were to graph this, you're going to get a semicircle with a radius of 2 centered at the origin. Sometimes I show that, but I'll spare you. So I promise if you throw this into your calculator, if you don't believe me, it's going to look like this. That's what this function looks like. If you look at your limits, though, we only want the area enclosed by that function from 0 to 2. So we're really only looking for this area in here. Just like number 14, where you had a rectangle and then a triangle. What we have here now is basically a quarter circle. So we know the area of a circle to be pi r squared. But since this region that we're concerned about from 0 to 2, so just this is a quarter of a circle, we would just take pi r squared, multiply it by 1/4. This circle has a radius of 2. So 2 squared is a 4 times a 1/4 should just give us a 1 pi. That's the area of that little segment there, that quarter circle. So this has a value of pi. And then that's it for 15. But again, keeping in mind value versus area, those currently would have the same answer. The value is pi, the area would also be pi. 16. Let's draw in the function y equals x. So if I come down here, y equals x would have a y-intercept of 0. Let me move this just a little bit here. Yeah. And again, I'm just graphing y equals x since that's our function. And then it has a slope of 1. So if we were to sketch that out, looks like this. If I connect those, we're dealing with this line. And we want the area from -3 to a +2. So traditionally, some people just have a hard time seeing this. What you have to always understand, we are looking for the area between your function, here's our function, and the x-axis. So the area between this function and the x-axis starting at a -3 would be right here. But then eventually we have to flip over to the other side. We still need to get to 2. That would be in here. Still some geometry. These are basic triangles. So if I treat this as a triangle, I have a base of 3, and then this is a height of 3, so that's 9. And then we want half the base and a height in a triangle. So half of 9 is 4.5. But since we are underneath the x-axis, we assign a negative value to that. We need to continue on to 2 because that's our upper limit. That's also a triangle. We have a base of 2 in this triangle, a height of 2 in this triangle, so that's 4. And then we would want half of 4, which is 2. Since it's above the x-axis, it takes on a positive value. Since we are, again, and here's now where it does become important, since we are looking for the value, we're trying to evaluate an integral, which basically means find the value of, what we would do is take this -4.5, and when we're doing value, we just add those up, and that should give us a -2.5. So our answer here, -2.5. Here's why it's important to know if we're looking for a value or an area. If I was doing the area, so it's up to you if you write this down on your paper, you would have taken the positive area of 2, you would have subtracted this negative area of 4.5, so that we ultimately would say we have 6.5 units of area enclosed if that's what I was asking. I'm not, that's why this is our answer, but notice how these are very much different, okay? Last one, 17. This is the function absolute value of x minus a 2. So our vertex is down here at a -2. If you remember, this is our v. So it would initially look like this. However, we only want the area enclosed by this function in the x-axis from 0 to 5. So starting at 0, I would be dealing with this area here, and then I'd have to stop at 2, because after 2, I go above the x-axis, and we would want all the area up until 5. And again, we're just doing that because those are our limits, from 0 to 5. 2 triangles again. So if I do this first triangle, the yellow triangle, it's a 2 by 2. So that's 4, half of 4 is 2. Underneath the x-axis means we assign a negative value to it. If we do the green triangle has a base of 3 and a height of 3. So that's 9. Half of 9 is 4.5. We're again looking for the value. So we're just going to add these guys up. That should now give us a positive 2.5. Again, if I was looking for the area, we would have done the positive area of 4.5 and subtracted the negative area of a -2. And we would have said the area of this one is 6.5. So these actually would have had the same answer if we were doing the area. But since we're doing the value, one's a -2.5, one's a positive 2.5. All right, so I'm going to cross these out just so we know that's not what we're doing in this problem. But if I did, that's how you would have to evaluate those areas. Last one, number 18. I want you to write an integral or integrals. So that probably implies there's going to be more than one. That would give you now the total area. So now I do want you to find the area. So I don't want a value. I want you to find the total area of the region enclosed by this curve, which I show below on your paper. You can see it right now. It's on my next page. And we're going to do that area underneath this curve from a -2 to a +1. So if we go down to that, I don't know why this did not translate. Let me sketch this in real quick. And then you should see in yours an area shaded here. And then in here. All right. All the way up to here. We go to set up our first integral. So do your integral sign. Do this in black. The first integral would have started at a -2. And the reason I'm starting at a -2 is just because I tell you to start here at this -2. And that first region would extend to a -1. We're trying to find the area enclosed by this curve, so we do x squared minus a 1, and then your dx. Then we do another integral, because here we had an area above, down here we have an area below. So now I'm going to go from a -1 to a +1 for the area that's below. Same curve though, so x squared minus a 1, and then our dx. When we learn how to evaluate this, which we can't do, we don't know how to do that just yet because this is not a constant. This is also not a triangle. It looks somewhat like a triangle, but it's not. So we can't do geometry like we did in those previous 4 questions. Same here, this is not a semicircle, even though it might look somewhat like a semicircle. This is not a geometric shape, neither is this one up here. So we can't do simple geometry. That's why we're only able to set up these integrals. But if we did know how to evaluate this, this would have a positive value because this area is above the x-axis. And when we learn how to evaluate this one, that's going to have a negative value because this region is underneath the x-axis. Like I've done now in those previous couple, if we're looking for area, which we are, this one I do specifically say I want the area, we take the positive area above and we would subtract the negative area that's below. So here is how we would want to write this using 2 different integrals and allowing us to figure out our total area, which is why we're going to be ultimately subtracting the negative integral. Hopefully that makes some sense. If not, see me second period. This traditionally is not real hard. I think I can get you squared away pretty quickly. If you did have some questions on any of this, feel free to stop by second period. So with that, that is it. We'll see you guys tomorrow. Have a good night.